Hey everybody, we are going to do some graphing of rational functions with calculus, at least the first derivative, and this is an example from the homework, and I already got an email saying, hey, negative signs are confusing. And they are, especially at this level. So, first thing I'm going to do with this rational function is factor it. Sometimes when I'm staring at all the factors, it really helps certain things leap out. Now, notice what I did with the negative sign that was in the front. I decided I would like it better as a -1 factor all by itself up in the numerator. Could have also put it in the denominator. Could have left it out front, but this is what's most helpful to me. Now, as I go through my process of figuring out the various qualities of that this graph is going to have, I'm going to start with the simplest one, the y-intercept. F of 0. Put 0 in for x and I get -0 squared over 3 times 0 plus 2, which is 0. I could have stopped at just noticing that the numerator would be 0, but please remember to double check that fractions equal to 0 when 0 is in the numerator, but it can't also be 0 in the denominator. What we're really talking about is when we go looking for x-intercepts here. Okay, we're looking for what makes the numerator equal to 0, and that's when x equals 0, but we have to make sure that same factor doesn't also occur in the denominator. Okay, then you have a removable discontinuity, you have to graph a hole, that's an entirely different thing. Now, that's our only x-intercept apparently. Now let's look for the vertical asymptote, which is whatever makes the denominator equal to 0, again, as long as it's a unique 0. As long as that 0 only occurs in the denominator, does not also occur in the numerator. And it looks like x equals -2 is the only value of x that will make the bottom of this fraction equal to 0. And it does not also make the numerator equal to 0, so we're good. End behavior. Now, end behavior in general, as you guys know, is the limit as x approaches infinity of what y is doing, and at the other end, it's the limit as x approaches -infinity of what y is doing. And we went over some rules for when it's the same degree top and bottom, when it's a larger degree polynomial on the bottom, but this one has a larger degree on top, larger by 1. That means it will be a slant asymptote, and we have to break out our polynomial long division. Now, I'll keep the negative sign there, and I will write the 3x plus 6 out here. Notice I'm not using synthetic division. That's because of this 3. For synthetic division to work, it has to be a linear term on the bottom beginning with 1x. This one begins with a 3. Could I factor out the 3? Sure, but you know, this isn't that much harder, and it's just easier than keeping track of what I factored out. Same thing with the negative. Let's just leave it here and see where that goes. Get the slant asymptote all in one big long division step. I am going to write my plus 0x plus 0, my placeholders over here. And now I think I'm ready to begin by asking myself, what do I multiply times 3x to get -x squared? And the answer is -1/3 x. -1/3 x times 3x will get me -x squared, which is what I want. I'm going to open my parentheses, put my subtraction sign, because I know that's coming up. Now, I can't stop with just getting rid of this x squared term. I have to distribute this -1/3 x to the 3x and to the plus 6. -1/3 x times 6 is minus 2x. So when I work out this subtraction, -x squared minus -x squared, okay, these went away like I wanted. 0 minus -2x is positive 2x. Okay, and now I bring down my plus 0. Now I ask myself, what do I multiply 3x by in order to get 2x? And that answer is plus 2/3 x. If I multiply 2/3 x, whoops, I apologize, that answer is just 2/3. If I multiply 2/3 times 3x, the 3 here divides out with the 3 there, the 2 remains, the x remains, I will get 2x, which is what I wanted, because I need 2x minus 2x, I need that to go away. But I still have to distribute the 2/3 and multiply it times the plus 6, which gives me plus 4. So when I subtract, 2x minus 2x goes away according to plan. 0 minus 4 gives me a remainder of negative 4. So what I've just demonstrated is that y could also be written as negative 1/3 x plus 2/3 minus 4 over 3x plus 6. Now, as x approaches infinity, or for that matter, infinity or negative infinity, the denominator here will get as large as you can imagine, meaning the entire fraction will get as small as you can imagine. We can ignore this. We can totally ignore this, and our slant asymptote is just this line. Y equals negative 1/3 x plus 2/3. Not the prettiest line we've dealt with, but good enough. Okay. This is actually, I think, oh, we've got to do the sign analysis next. It's not quite enough information to even sketch our graph yet. Let's do some sign analysis. So let me get rid of all this. And I don't need that anymore. Get rid of this end behavior. And my sign analysis to see how this behaves. Okay. One thing I like to do, if there's a factor that's really simple, but it's going to bother me, even if it's so simple I shouldn't even have to do it, I include a number line for it. I am including a number line for the factor negative 1. Even though I know for all values of x, negative 1 stays negative. Negative 1 has nothing to do with x. Writing this number line helps me remember that this negative sign here is out in front. Now, other factors, the factors on the numerator are negative 1, x, and x, the way I've written it. But you know, x squared I'm less worried about. X squared, rather than write two number lines, one for each x, I'm going to write one number line for x squared, put my value of x equals 0 in the middle, and ask myself, when x is negative, what is the sign of x squared? Well, when you square a negative, you get a positive. When x is 0, well, 0 squared is 0. And when x is positive, you square a positive number, you still get a positive. I don't have to write a number line for my factor of 3, but if you want to be a completist, 3 is always positive. That's a little less worrisome to forget, though. My last factor I do have to pay attention to, and that is x plus 2, which is 0 when x is negative 2. X plus 2 will be negative if you put any value in for x that's less than negative 2, and x plus 2 will be positive if you plug in any value for x that's greater than negative 2. Now the point to this, and sometimes these vertical lines help me keep track of what I'm doing, the point to this is to finally make a last number line where we think about how all these factors behave. Number line for y itself. And we'll put negative 2 on it, we'll put 0 on it, and we'll ask ourselves, when x is less than negative 2, how does y behave? Well, when x is less than negative 2, y behaves as if you have a negative, multiplied times a positive, divided by a positive, and then divided by another negative. Because negative 1 is in the numerator, it's being multiplied by x squared, it's being divided by 3, and it's being divided by x plus 2. So we have a negative times a positive, divided by a positive, divided by another negative. Y will be positive. At negative 2, we have a negative times a positive, divided by a positive, and then divided by 0. So at negative 2, our function is undefined, because there's a 0 in the denominator. Between negative 2 and 0, we have a negative times a positive, divided by a positive, divided by another positive. Our function has to be positive. At x equals 0, we have a negative times 0. Okay, so it's 0. Doesn't really matter what we're dividing by here as long as it's not another negative. So our function will be 0 at that point. And it looks like for all values greater than 0, we have a negative times a positive divided by a positive divided by another positive. Our function will be negative for all those values. So what is this going to look like? Well, a quick sketch where I put my vertical asymptote in at -2. My horizontal asymptote was -1/3 x plus 2/3. So I'm just going to, I don't know, call that 2/3 and guesstimate that slope of -1/3. If I had actual graph paper, I'd be a little bit more careful. I know my function has a 0 and a y-intercept at the origin. Okay. Now, looking down here, this function has to be positive, and it should snuggle up with both of these asymptotes. So I'm thinking it looks something like that. Then it, I think I have a mistake here. Between -2 and 0, it looks like I have a negative, positive, positive, positive. Yep. I should have a negative sign there. Okay, sorry about that, guys. Hope it wasn't too confusing. But this also makes more sense, because, not going to lie, I already know what this graph looks like. Negative between here makes much more sense, because my function has to snuggle up to this vertical asymptote and be negative and hit the origin. And then it's got to be negative over here and snuggle up to that that slant asymptote. So my function should look something like this. Okay? Yeah, that matches my sign analysis. All right, now do I know that it really peaks here at the origin? And do I know that where does it actually turn around up here? Pre-calculus can't answer those questions for us, but calculus can. Now, this is not the most trivial derivative in the world. It's not the hardest either, but it does require the quotient rule. So our first derivative is going to tell us where our extrema are, or at least it's going to tell us where the horizontal tangent lines are. And figure out the rest from there, right? Okay, one thing I like to do with this negative sign again, which is really the source of most of the confusion on this problem, is I'm going to leave it here on the outside, and I'm going to do my quotient rule. I'm going to figure out my u prime v minus uv prime over v squared inside these brackets, and I'll deal with the negative sign at the end. So there's my u, there's my v, and let's go. So u prime is, go back to my more clear colors here, u prime is 2x times v is 3x plus 6 minus u, which is x squared, times v prime, which is just 3, all over 3x plus 6 squared. Okay? So that should be my u prime v minus uv prime over v squared. I think we need to simplify this just a little bit. So that's going to be negative 6x squared plus 12x minus 3x squared over 3x plus 6 quantity squared, which gives me negative 3x squared plus 12x over 3x plus 6 squared. Notice I didn't bother to FOIL or distribute out the denominator. On the quotient rule of polynomials, that's rarely a good idea. Maybe it'll disappear with a factor in the numerator on some problems. Usually doesn't tell you anything. Leaving it in this form is usually best. Now, this first derivative, what we're interested in is the horizontal tangent lines, because those are the likely candidates for where this function turns around. It's not always. There are functions that hit a horizontal tangent line without turning around, but in this case, nothing in this behavior suggests that. So this first derivative will equal 0 when the numerator equals 0. And this negative sign here really doesn't matter. And as long as the zeros I find in the numerator are not also zeros in the denominator, I can basically ignore the denominator and ignore the negative sign, and all I have to figure out now is when is 3x squared plus 12x equal to 0? Well, that will be, I'll factor out a 3x, I'll be left with an x plus 4, and I can see that the two x values that will make this equal to 0 are x equals 0, x equals negative 4. That means I have a horizontal tangent line here at the origin. And that makes sense. I mean, that's not a big surprise. If we go back to the sign analysis, we know that this graph had to be negative, then hit the x-axis, and then stay negative. So turning around there makes total sense. There's no way it goes above and is positive or anything else. So that's consistent. And negative 4, okay, it's completely reasonable to me that that horizontal tangent line, based on my graph, could be above an x value of negative 4. The only other thing I'm interested in is what is that y value. So I'm going to take this x value of negative 4 and plug it back into the original function, not the derivative. If you want to find the actual height of this point, not the slope of the tangent line, but the actual height, take negative 4, plug it into the original function, and what I will get is negative 4 squared over 3 times negative 4 plus 6. And that gives me 16, negative sign on the outside, negative 12 plus 6 over negative 6. That gives me positive 8/3. Okay, so the y value is positive 8/3 for that point. And we know that we have, well, another way to express this information is if I specifically said what are the extrema, the relative extrema of this graph, you would answer, as soon as you erased and made some room on your iPad, you would tell me that the interesting things about the extrema of this graph are, finally, okay, that there is a relative minimum at negative 4 8/3 and a relative maximum at the origin 0, 0. Now, if I really notice, the minimum is higher than the maximum on this graph. Relative minimum is just that, relative only to the points around it. Relative maximum is relative only compared to the points around it. So there's no discrepancy to a maximum being lower than a minimum on this graph. And if we really wanted to sort of punish ourselves, we could find the second derivative, go back and derive this again with the quotient rule, and prove we should see that the second derivative is always positive over here on this side of our asymptote. That would explain why this is smiling. And we should find the second derivative always being negative over here on the right side of negative 2, because the second derivative would always be negative here, if this is correct. But, as they used to say in the old textbooks, I'll leave that proof to the reader. Hope this helped.